Ever get that feeling of walking up a razor's edge, like trying to set your home security just right?
Oh, yeah. Too sensitive, and it's cats setting it off all night.
Exactly. Too sensitive stray cats. Not sensitive enough, and, well, you might miss the real deal.
Right.
That's kind of the core tension we're diving into today. This tricky balance between catching everything that's sensitivity and being right about what you catch precision.
And it's not just home security, is it? It's a huge challenge when we ask AI to make, important decisions.
Yeah, absolutely.
And what's really fascinating right now is how researchers are tackling this exact problem. One of the most promising ways. It's something called multi-layered AI models.
Multi-layered AI. Okay, sounds interesting. Maybe a bit techie for some. Why should we care? Is it just jargon, or is there something, genuinely insightful here about where AI is going?
Oh, it's definitely more than just buzzwords. Understanding this helps you see how we're trying step by step to build more trustworthy AI, especially for complex problems. We'll break down how these layered models actually work, why they often do better than just a single AI, and we'll look at some pretty surprising ways they're already being used out there. You might have some real aha moments about this.
Sounds good. So where are we getting our info for this? What sources are we looking at today?
We've got a really interesting mix. There's a detailed research paper from Coup Research that really gets into the nuts and bolts.
Right.
And we also found a great YouTube discussion that introduces the main ideas really clearly, very accessible.
Excellent. So our mission for this deep dive, what are we aiming to get our heads around with these multi-layered systems?
The main goal is to really understand how taking one big, complex problem and tackling it in a sequence of focused steps, almost like a really sophisticated filtering process, how that leads to AI systems that are more accurate, yes, but maybe more importantly, more reliable.
Okay, let's start there then. Why does a single AI model sometimes struggle with this balancing act? What are the sort of built-in limits?
Well, the fundamental challenge, like you said, with the security system, it just boils down to that constant push and pull, sensitivity versus precision.
And that trade-off.
Exactly. Single AI models often face this dilemma: be super sensitive and you get flooded with false alarms, or be really precise and risk missing important signals.
Right, it feels like you kind of have to pick one to prioritize with just a single system. You can't easily max out both.
That's pretty much it. With one setting, the AI has to compromise. It's baked in. Our sources really emphasize this inherent trade-off.
And I bet this gets even trickier when you're dealing with really complex problems, right? Lots of data, subtle patterns.
Absolutely. In those really complex scenarios, a single model might only, effectively learn from a small fraction of all the information it's given. It's like trying to understand, I don't know, a really complex historical event by just reading chapter 3. You're going to miss a ton of crucial context.
That's a great analogy. You just don't get the whole story, all the different angles. What about uncertainty? Like, if the initial data is a bit fuzzy,
Yeah.
can a single model easily change its mind as it gets more clues?
That's another key issue. Single models often make an initial judgment, right, based on what they see first, but they don't really have a built-in way to easily revise that if new information comes along later.
Oh, okay.
It's hard for them to kind of go back and say, hold on, this new clue suggests maybe my first idea was off. They lack that iterative refinement capability.
Okay, so single models grapple with sensitivity versus precision, complexity, and adapting.
Right.
That really sets the stage for why this multi-layered idea might be better. You called it a step-by-step filter. How does that actually work?
Yeah, the core idea is simple, really. You take that one big, tricky decision and break it into a sequence of smaller, more focused steps. Each layer or stage has a very specific, manageable job.
Okay.
And our sources pointed to a pretty common pattern, often 3 stages. Think of it like a series of specialized filters, each one refining the information a bit more.
3 stages. Got it. Let's unpack stage 1. What's the goal there?
Stage 1 is all about casting that wide net, comprehensive detection. The main aim is to capture everything that could potentially be relevant. Even if that means grabbing some stuff that turns out to be noise later, the false positive.
Right.
The absolute key here is high sensitivity. You really don't want to miss anything important in this first pass. Minimize those false negatives.
So, priority 1. Don't let anything slip through, even if it means a bit of cleanup later.
Exactly that. It's intentionally a bit over-inclusive just to be safe. Like an initial medical screening test, it might flag several things as potentially worrying, even if most turn out fine. It's designed to be broad.
Okay, makes sense. Cast the wide net, then stage 2 comes into what? Sort through the catch?
Precisely. Stage 2 is about error removal, refinement. The goal here is to start filtering out those false positives from stage 1 and reduce the overall uncertainty. It's like an intermediate check. Think about your email spam filter. After a basic first scan, maybe a more clever second filter looks for specific patterns to pull out legitimate emails that got wrongly flagged as spam initially.
Ah, okay. So getting more selective, narrowing things down,
Yeah.
which leads us to stage 3.
Exactly. Stage 3 is about precise confirmation, high confidence. The goal here is to make a really accurate final decision with very little uncertainty left. This is where you eliminate any remaining false positives.
Okay.
Like the final step in credit card fraud detection, after initial alerts, maybe some analysis, this stage says, yes, definitely fraud, or no, definitely okay, with high confidence before they actually block your card.
That clicks. It really is like a funnel, isn't it? Starts wide, gets narrower and more accurate each step. I think one of the sources had a simple calculation for this.
Yes, it did. And it shows the effect quite well. Let's say, hypothetically, you start with 100 items. Stage 1 being broad, flags maybe 95 is potentially interesting.
Okay, catches most things.
Then stage 2 looks at those 95. It's designed to refine, maybe it keeps around, say, 84% of them, filtering out the clearer errors.
So we're down to about 80 items then, roughly. It's a decent reduction.
Right. Then stage 3 takes those 80. With its focus on high precision, it might confirm about, let's say, 88% of that group are truly the items of interest.
Which brings us down to around 70 confirmed items from the original 100.
Exactly. So you can really see how the layers work together to dramatically filter down from that initial broad sweep to a much more refined, reliable set of results.
Wow, okay. So even if each stage isn't perfect on its own, the combined effect is much sharper. You end up focusing on the most likely correct answers.
That's the idea. It really shows how they build on each other to boost the overall accuracy and, crucially, the reliability.
Okay, this sounds really promising in theory. How does it play out in the real world? Did the research give us some solid examples?
Oh, yeah, absolutely. Our sources had some great ones. Let's take airport security, going through the TSA checkpoint.
Yeah, the x-rays, the pat-downs, the whole thing. Always fun.
Right. So think of stage 1 as that initial x-ray for your carry-on. Studies suggest it can have really high sensitivity, maybe around 98%. It's great at flagging anything that looks even slightly odd.
Okay.
But the precision might be pretty low, maybe only 15%, which means it flags tons of harmless stuff.
Makes sense. My water bottle, my laptop.
Ah,
Seems like my bag always gets pulled aside.
exactly. That's stage 1, doing its job, high sensitivity, low precision. That flag then triggers stage 2, the manual check.
Right, the officer opens the bag.
Yeah, takes a closer look. This stage, the manual check, might have medium sensitivity, maybe 85%, but much better precision, perhaps around 70%. They're way better at figuring out if that blob is a threat or just, your toothpaste. They rule out lots of those initial false alarms.
Okay. And is there sometimes a third stage too?
Yeah, potentially. If there's still some doubt after the manual check, they might use more specialized tech, like those swabs that test for explosive residue.
Right.
This stage might have medium sensitivity, again, say 80%, but really high precision, maybe 95%. It's for nailing down those tricky cases with high confidence.
So when you step back and look at the whole system, x-ray, manual, maybe swab, the overall performance is quite different from just that initial scan.
Totally different. The overall system might achieve something like, say, 66% sensitivity, still pretty good at catching threats, but with a very high 95% precision.
Ah, I see.
The goal is to balance catching the bad stuff with minimizing the chaos of pulling everyone aside for harmless items. It's about strategically managing those trade-offs across the layers.
That really clarifies how the different stages work together for a better overall balance. What about a medical example? Did the sources mention anything there?
Yes. Breast cancer screening is another classic example. Stage 1 is often the mammogram. Research suggests it can have high sensitivity, maybe 95% in some studies, good at spotting potential issues.
What?
But again, precision can be lower, maybe around 12%, which means, unfortunately, a lot of false positives, things that look suspicious but aren't actually cancer.
Which must cause a huge amount of stress and lead to more tests, right?
Exactly. And that often triggers stage 2, which might be an ultrasound. This usually has medium sensitivity, say 90%, but better precision, maybe 50%. It helps clarify those ambiguous findings from the mammogram, give doctors a clearer view. And if things still look uncertain after the ultrasound,
Then stage 3 is often a biopsy. Now, this is more invasive, obviously, but it provides very high sensitivity, like 98%, and extremely high precision, maybe 99%. It gives that definitive diagnosis.
So same pattern as airport security, really. Look at the whole process together, and the final numbers are much better.
That's right. The overall performance for this layered screening process might end up around 84% sensitivity and 99% precision.
Impressive.
It really is. The system prioritizes not missing a potential cancer that's the high overall sensitivity, but it also drastically reduces the number of women undergoing unnecessary invasive biopsies due to false alarms. That's the very high overall precision. These examples really drive home the practical value, especially when the stakes are so high.
Okay, so zooming out a bit from the examples, what are the core advantages? What makes these layered systems work so well?
Well, the research points to a few key things. First, as we saw, is this idea of specialized roles. Each layer gets really good at its specific job.
Right.
One paper put it nicely. Stage 1 is like the search party, finding anything potentially relevant. Stage 2 is the analyst, sifting through it, removing the noise. And Stage 3 is the judge, making that final high-confidence call.
That spiralization makes intuitive sense, lets you optimize each step for what it needs to do.
Exactly. And that generally leads to better overall results than one generalist model trying to juggle everything. It's like a specialist team versus one jack of all trades.
Makes sense. What else? Any other big advantages?
Another really important one is how it lets you manage the cost of errors more strategically.
How so?
Think back to the cancer screening. A false negative missing a cancer is way worse than a false positive doing an extra test, usually. This layered approach lets you design each stage to minimize the most harmful kind of error at that point. So maybe you tolerate more false positives early on to absolutely minimize false negatives.
Oh, that's clever. It's not just about overall accuracy, but about being smart, about which errors are more acceptable where.
Precisely. And then there's this idea of gradual information refinement. Each stage builds on the last one, step by step, reducing uncertainty. It's like focusing a blurry picture. Each layer brings the answer into sharper focus, boosting confidence in the final outcome. Sort of like Bayesian updating, if you're familiar with that.
Right, updating your belief as you get more evidence. And I think one source mentioned this mirrors how we humans often make complex decisions.
It did. Think about how doctors diagnose things. You might have a general checkup, that's Stage 1. If something's off, maybe more specific tests or scans, Stage 2. And if it's still unclear, maybe a specialist consult, Stage 3. It's a very similar step-by-step process.
Yeah, that's a great analogy. We often do that instinctively. It makes the AI approach feel less abstract. Now, we've talked about single models. How do these multi-layered models compare to other ways of using multiple AIs, like ensemble learning?
That's a really important distinction. Ensemble learning also uses multiple AI models, but it works differently.
Okay.
In ensemble learning, you typically train several different models, often independently, maybe on different data subsets. Then you combine their predictions right at the end, maybe they vote, or you average their outputs. They usually work in parallel.
Okay, so like getting a bunch of opinions and averaging them out at the end. How's the multi-layered different then?
Multi-layered models work sequentially. The output from Model 1 feeds into Model 2 as its input, and so on down the line.
Like a pipeline.
Exactly. It's a pipeline designed for refinement. Information gets processed and improved as it moves through the layers, rather than just combining separate final answers at the very end. Sequential refinement versus parallel combination.
Got it. That sequential part seems key to the filtering and refinement we've been discussing. Now, these layered models sound powerful, but surely there are downsides or things you need to be careful about when building them.
Oh, absolutely. The research definitely flags some important considerations. They aren't magic. One big one is error propagation.
Gee.
If an early stage makes a mistake, especially a false negative where it misses something important, that mistake can just carry right through. The later stages might never even see the information that was missed early on.
So if stage 1 misses something vital, stage 2 and 3 can't fix that because they never get the chance. Kind of a missing information in that missing information out problem.
Exactly right. Another key thing is resource optimization. How you use your computing power.
Okay.
You probably want faster, maybe simpler models for stage 1 because it's handling a huge volume of initial data. Then you can deploy your more powerful, maybe computationally heavier models for stages 2 and 3, where you're dealing with fewer, more targeted cases. You have to be smart about allocating resources.
Right. Efficiency matters. Anything else to keep in mind?
Yeah, feedback loops. These can be really valuable. The idea is if you detect errors in the later stages, you feed that information back to help improve the earlier stages.
So the whole system learns over time.
Exactly. creates a continuous improvement cycle for the entire pipeline. It learns from its mistakes at every level.
That makes a lot of sense. Okay, so we've covered single models, the layered approach, examples, pros, cons. Let's dig into some of the specific research mentioned. There was talk of meta AI and a 9-model architecture. What's that about?
Okay, yeah, this is where it gets really interesting. So in this context, meta AI refers to a specific framework. It's about evaluating AI reliability by demanding agreement consensus among multiple independently trained models.
Yeah.
And the research really highlights a crucial finding. Single AI models, the kind that learn patterns from data, are inherently a bit unstable. They can produce inaccurate results, especially when they see something new, something outside their training data.
So they can be easily tripped up by the unexpected.
Pretty much. And importantly, they often can't tell when they're wrong. They might be confidently incorrect.
Right.
So the core idea of this meta AI approach is only trust a result if multiple different AI models trained independently, maybe with different data, different architectures, all consistently agree on the answer for the same input.
It's like demanding a second, third, even ninth opinion before you believe it.
That's exactly the idea. The thinking is, any one AI might be fooled, but it's much less likely that a diverse group of AIs will all be fooled in the same way at the same time. The wisdom of the diverse AI crowd.
Okay.
The Coup research paper goes into the stats, showing that for tasks like defect detection, single models often produce more false positives than true positives. Basically, they flag more normal stuff as abnormal than they correctly identify actual problems.
Wow, that's quite a finding.
Yeah.
That a single AI might be more likely to cry wolf than find the wolf.
It is. So to combat this, the researchers built this 9-model architecture, and the key is diversity within those 9 models.
How so? Different types.
Yeah, exactly. Architectural diversity, using different kinds of neural networks like CNNs, transformers, etc., which learn differently. Scale diversity, using models of different sizes and complexity. And data diversity, training them on different samples or amounts of data.
So they aren't just 9 clones. They have different perspectives, different strengths.
Precisely. The idea is, if one type of model is susceptible to a certain error, another type might not be. The consensus becomes much more robust.
Okay, so how do they get to a final answer from these 9 diverse models?
They set specific rules, boundary conditions. One is an agreement threshold. At least 6 out of the 9 models have to agree on the outcome.
6 out of 9. Why 6? Seems specific.
They found through testing that requiring agreement from at least 6 models significantly increases the probability that a flagged issue is a real issue. It dramatically boosts the reliability compared to just one model, or even just a simple majority. 6 seem to be a good balance point.
Okay, that makes sense. Strong majority needed. Is that the only check?
No, there's a second step. Confidence filtering. If they get at least 6 out of 9 agreement, they then looked at the average confidence score of those agreeing models.
Oh, how sure are they?
Exactly. If that average confidence is high, say above 90%, then the result is accepted as reliable. If the agreement is there but the confidence is lower, it might get flagged for human review or used as a tricky case to help retrain the models.
So it's not just do they agree, but also how sure are they about their agreement?
Precisely. And this multi-model framework inherently helps catch common AI failure modes too, like problems caused by bad training labels, or when the dividing line between 2 categories is really fuzzy. If one model learned something wrong, the others likely didn't, so they won't agree, and the issue gets flagged.
That makes sense. The diversity acts like a built-in error checker. Now, the sources also mentioned boundary conditions and handling undefined samples. What's that referring to?
Boundary conditions are basically when the AI encounters input data that's significantly different from what it was trained on, stuff it hasn't really seen before.
Okay, novel situations.
Yeah, and the system handles these by marking the sample as undefined. This happens if the models disagree fewer than 6 agree, or if they do agree, but their combined confidence is too low.
So instead of guessing, it just says, I don't know.
Essentially, yes, it signals uncertainty and flags it for review. It's saying, I'm not confident enough to make a call here, let's get a human involved or learn more about this.
Does the research give examples of this?
It does. The Coup paper had several, like an image labeled Subway, the food place, got confused with Subway, the metro, because of bad training data. The models disagreed, marked it undefined. Another was a picture of a lamp that looked really unusual compared to the training lamps. Only 5 models agreed on lamps, so it became undefined, avoiding a forced, potentially wrong classification.
Okay.
Another example was an image of a valley that looked a bit like a lake and a river. The models gave mixed results, couldn't reach the six-model consensus, so again, undefined. It shows the system identifying ambiguity.
So the disagreement or low confidence really acts as a warning flag in these tricky cases.
Exactly. But it's not foolproof. The paper also showed a critical failure. An image of a lime, something the models hadn't been trained on at all, was confidently misclassified as a lemon by all 9 models with 100% confidence.
Oof. So even with 9 models, if none of them have seen anything like it, they can still all agree on the wrong answer.
Yes. It underscores that even this advanced approach still fundamentally relies on the quality and breadth of the training data. If there's a blind spot in the training, the consensus can still be wrong.
So it's a big improvement, but not magic. It still needs good data.
Definitely. But the core message bringing it all together is how these multi-layered or multi-model approaches cleverly manage that sensitivity-precision trade-off. By breaking down the problem sequentially or by demanding consensus from diverse viewpoints, you end up with a system that's generally much more robust and reliable than a single AI trying to do it all.
And this isn't just theory, right? This kind of thinking is being used more and more in important areas: healthcare, security, finance stuff that affects us directly. Understanding it helps us see how we're working towards AI we can actually trust more.
Absolutely. It highlights that AI reliability isn't just about hitting a high score, but about the process and how the system handles uncertainty.
So as we wrap up this deep dive, here's something to chew on. If we crank up the sensitivity to the max in those early stages, aiming to catch every single potential risk,
Yeah.
how much noise, how many false alarms are we actually willing to tolerate?
Yeah.
Where's that line between ensuring nothing vital gets missed and accepting potentially a lot of initial inefficiency or even chaos? Seems like there's another really important trade-off baked into designing these systems.
That's a fantastic question to end on. This look at multi-layered AI really shows a fascinating path forward for making AI more reliable. The principles, sequential refinement, the power of diverse agreement. They offer valuable lessons, maybe not just for AI, but perhaps even for how we tackle complex choices ourselves.